Good morning, or maybe good evening if you are watching this presentation from a different part of the world. My name is Barbara Lubelli. I'm Associate Professor at the Delft University of Technology in the Netherlands. And in this presentation, I will report on the results of the Technical Committee 271, which worked on the development of an accelerated laboratory test to assess the durability of material with respect to salt crystallization. Salt crystallization is a common cause of damage for many different building materials, very often in historic construction, but also in new buildings. Salt damage may affect different materials in many different climates. Material with a high mechanical strength may still be subjected to salt decay, and damage occurs in hot as well as in cold climates and in humid as well as in dry environments. As salt damage is such a common type of damage, you can imagine that it is important to be able to estimate or at least to assess the durability of building materials with respect to salt crystallization. Unfortunately, decay due to salt crystallization is a very complex process, more complex than other processes such as, for example, frost damage. Due to its complexity, modeling and simulation of the process require an input of several data ranging from material properties to environmental conditions. This has made difficult to use modeling to estimate buildings' durability with respect to salt crystallization. There are models, they exist, they are also quite good developed. We use them in the TC, but in the field of conservation and construction, these are rarely used. More often, in order to assess the durability of materials with respect to salt crystallization, when this is not known from past experience, then laboratory, they use accelerated aging test. And there are several procedures for accelerated tests. There is a European standard for salt crystallization test. There are 3 RILEM recommendations already. There are other recommendations from other institutes. But if you look in the literature, you see that every researcher is developing his own procedure. And even in practice in the field, people is using sometimes different procedure. This is mainly coming from the fact that this standard, they are not considered always representative of the field situation. And the consequence is that there is not possible, it's very hard to compare the results. So every time you need to start again. And main limitation of this existing accelerated tests are the fact that they are not always considered reliable, as I mentioned, because the damage type that you get in this test might be different from what you see on the same material in the field. Also, the severity of the damage may be different. For example, some tests using sodium chloride, they are not able to develop damage within the time of the test. Within a few months. So while you know that in the field, a lot of damage is present in the presence of sodium chloride. And some of these tests might be very time consuming. So the more representative they are, the more complex they are, the more time consuming regarding the procedure, but also they can be time consuming because before you see damage, it can take several months. So starting from this limitation, the RILEM TC 271 was set up in 2016 with the aim of improving the existing procedure and to develop a new improved procedure for assessing durability of materials with respect to salt crystallization. Since then, more than 30 researchers worked in this committee, and the committee is now in its final stage. The work of the TC developed in different steps. First of all, we did a literature review of existing tests, laboratory tests, and also of theoretical models. We publish open access 2 papers regarding this literature review. So if you are interested to read more, you can download the paper from the web. Then we also collected field data, which were used as input for the test procedure. For example, data regarding the amount of salt which are found in the field, in materials, And also we collected data on type of damage in order to use them for validating of the test procedure. So to see if the damage we get with our procedure is similar to the damage which is observed in the field. Most of the time, research was devoted to experimental and modeling work. And at the moment, we have a procedure we have tested already on 2 substrates, and we are now testing on 8 additional substrate in a round robin test, which is ongoing and is going to finish in a few weeks. We plan to publish the test procedure in Materials and Structure in 2022. Regarding the scope, as I mentioned, the procedure wants to assess the durability to salt crystallization by accelerating the process without altering significantly its mechanism. And the idea is that based on the result of the test, the user should be able to define the durability ranking of the different substrates which have been tested with respect to salt crystallization. The focus of the test is to reproduce salt damage triggered by capillary transport of salt solution and evaporation at the surface. So it means that we focus on that process, which is in practice, we would say, rising depth of groundwater. So groundwater can be considered as kind of diluted salt solution. And this process is the process we are going to reproduce. We are not going to study processes related to sea salt spray because in this case, there are already standards which are commonly accepted. We also focus on single material. At the moment, we have tested different natural stones and bricks. The procedure may be adapted in the future to be used also for combinations of material, like in masonry, mortar and brick, or mortar and stone, or for plaster masonry combination. The users, so the target group, are laboratories in the field of renovation and construction. So that means that the feasibility is a main requirement in the definition of the procedure. So the procedure should be as simple as possible, should be feasible by laboratory, otherwise nobody will use it. We think that researcher probably will still need to have an adapted procedure to validate the theory, but we want to have this procedure for the field, for the practice. Regarding the approach, the selected approach is different from all existing accelerated salt crystallization tests, and it originates from the field of the concrete durability. It is known that in order for salt damage to occur, a certain amount of salt needs to accumulate in the pores of the material, so a certain degree of pore filling is necessary. And from that point, then the dissolution and crystallization of the salt will lead to development of the damage. So based on this idea, we develop a test which is made of 2 parts. So in the first part, the accumulation stage, the salts are accumulated in the material without occurrence of the damage. So, and afterwards, the dissolution crystallization cycle are generated in order to cause damage. So in the propagation stage, the salt amount does not change. It's just that the salt is dissolving and crystallizing, and this cycle will lead to damage. The work of the committee has been therefore also divided, the experimental part divided in 2 parts. So we focus first on the development of the accumulation phase and then on the propagation phase, and then we brought these 2 parts together, and we defined a draft test procedure which we tested on 2 types of limestone, a Maastricht and a Minier limestone, which are very different for porosity and pore size. And now we are testing the same procedure on 8 different substrates at different laboratory in a round robin test. We will fine tune the procedure in the coming months, and we will publish it in 2022. In the next slide, I will describe the details of the procedure as it is now. The specimen, so it's the first thing we needed to define. We considered a size cylinder specimen with a size of 50 millimeter diameter and 50 millimeter high. And we found this size a kind of compromise, a good compromise between the need to reduce the size of the specimen in order to speed up the test and the need to have a specimen which is representative of the variation of the substrate on site. So in this way, we think the test is still feasible, and is also still feasible in the case we want to use a combination of mortar and brick, for example. Regarding the minimum number of replicates, also in this case, it was a compromise. It's a compromise between the need of having, consider the variation present between the substrate, present in the substrate, and also the need of keeping the test feasible for the labs. And regarding the preparation, so we selected a cylindrical shape in order to avoid corner effects, but also because it is easier to wrap the lateral sides with the parafilm we used. We decided to use a film instead of liquid paraffin to avoid penetration of the paraffin into the pores, and also to make easier to remove the film at the end of the test and check the damage. Regarding the salts, we decided to use single salts in order to limit the complexity of the test. Besides, according to the literature review we did, salt mixtures are often less damaging than single salts. So despite we know and we are aware that in the field more often salt mixtures are present instead of single salt, because of this reason we decided to use single salt, and we think it's representative enough. Regarding the type of salt, we decided to use two salts, sodium sulfate and sodium chloride, and to develop the procedures for these two salts. For generally, salt crystallization test procedures, the standard, for example, the European standard considers only sodium sulfate, but we think that the two salts are so different that also in the type of damage they cause, that is necessary to consider the two salts, and also to maybe consider difference in the procedure depending on the type of salts. Both sodium chloride and sodium sulfate are salts which are commonly present in the field, and they are also sometimes used in laboratory tests. They are salts which have different properties. So for example, sodium sulfate has hydrates, while sodium chloride does not have any hydrate at room temperature above 0 degrees. And also the solubility of sodium sulfate is dependent on temperature, whereas the solubility of sodium chloride does not depend on temperature. The salts do also produce different damage. Generally, sodium chloride leads to powdering of the surface, while sodium sulfate is observed more often to lead to scaling or spalling. Because of these differences, we decided to test both salt and to develop two procedures depending on the type of salt. Regarding salt solution concentration, this was one of the most complex points to be solved in defining the procedure. So we had to decide first of all if we wanted to have a constant amount of salt expressed as percentage of the dry weight, or if we wanted to use a constant salt solution concentration. Finally, after testing and discussing, we decided to use a constant salt solution concentration because in this way we are more reproducing the situation in the field in which a substrate will absorb the same type of solution. For example, groundwater can be considered a diluted salt solution. And the amount of salt which will accumulate in the stone will depend on absorption and drying behavior of the stone. So, and also using a constant salt solution concentration facilitate the procedure, so increase the feasibility of the procedure. We decided to use 1 and 5% concentration in the case of sodium sulfate, and 5 and 10% concentration in the case of sodium chloride. This difference is due to the different aggressiveness of the test of the salt, and has been decided in order to have a solution which is salt content which is still high enough to produce damage, but at the same time still realistic based on the data we have from the site. And also, what we wanted was to avoid a too high concentration of the solution, because if we would use a very concentrated, saturated solution, for example, then the transport to the surface and the accumulation of the salt in a thin layer of the material would be more difficult, because the solution will the salt will crystallize early in the drying process. Then define the size of the specimen and the amount of salt. We started with the accumulation stage. So the accumulation stage is the first part of the test. And in this, the aim of this part of the test is to accumulate the salt in the outer thin layer of the material. This in order to reproduce the salt distribution which is present in the field, but also to obtain a high degree of pore filling, which is a condition for the occurrence of the damage. Besides, if the salts are present in the outer layer, they will be more sensitive to relative humidity and temperature changes. Regarding the contamination procedure, this has been selected after testing different contamination procedures. This phase took quite a lot of experimental work. We tested 3 different contamination procedures. Procedure 1, in which the salt crystals are positioned on top of the specimen, and then the relative humidity is increased and the salt solution penetrates into the pores. The second procedure consists in immersing the specimen into a salt solution, and at the same time, the specimen can dry at the surface. So it's a simultaneous capillary absorption and evaporation. The third procedure is a procedure in which the specimen is first contaminated with the salt solution, and then the bottom is sealed and the specimen can dry from the top surface. And this contamination has been repeated, this wetting and dry has been repeated several times. In order to make a choice, we use some criteria. So what we wanted to have was to accumulate the salt in the outer layer of the specimen. We didn't want to have any damage at the end of the accumulation stage, as the damage should occur only in the propagation phase. And we didn't want to have any efflorescence on the surface of the sample, because this would mean that less salt are left in the pores to produce damage, and also would make differences. The difference between the specimen would make difficult to compare the result. And also we look at the ease of execution of the different contamination procedures. At the end, we decided for procedure 3, which is consisting in contamination via capillary absorption through the bottom surface of the specimen and drying through the opposite surface. We selected this because it gave the best result regarding salt accumulation. Most of the salt were accumulating in the outer 1 millimeter layer, so leading to theoretically to a high pore filling, degree of pore filling. And also we didn't observe a lot of efflorescence at the end of the accumulation stage. The accumulation stage ends when the specimen has dried almost completely, when 80% of the introduced water has evaporated. At the end of the drying period, before starting the propagation phase, then the specimens are photographed and the damage is reported, is evaluated, if present. The second part of the test consists in the propagation stage. The aim of this stage is to lead to the gradual occurrence of the damage in such a way that the stones, the different substrates, can be ranked according to their durability. So we don't want damage to occur all in the first cycle for all the stones and all the salt concentration and all the salt site, because this would make difficult to rank the durability of the substrate. The propagation state is different depending on the salt type. This because the 2 salts we selected are damaging at different temperature and relative humidity conditions. So in the case of the sodium sulfate, damage mainly occurs when you re-wet the specimen with liquid water. This because the thenardite, the anhydrous sodium sulfate, dissolves and then recrystallize immediately into mirabilite, crystallizing at a high supersaturation. And this high supersaturation leads to high crystallization pressure and to damage. That's the reason why we decided in the case of sodium sulfate to re-wet the specimen with liquid water by capillary absorption from the bottom and at 20 degrees. Regarding sodium chloride, it is known that a lot of damage can be produced by simply let the salt dissolve at high relative humidity and recrystallize again at low relative humidity. So relative humidity cycle that can be very effective to cause damage in sodium chloride contaminated specimens. So if you just place the specimen in a high relative humidity environment, the salt which are present in the outer layer of the specimen will dissolve. And then when you lower the relative humidity again, the salts will crystallize. So you don't need to re-wet completely the specimen, and you can speed up the process. You can produce several relative humidity cycle and several dissolution crystallization cycle in a short time. So the test for sodium chloride consists mainly in those cycles, plus a re-wetting by capillarity from the bottom surface in order to retransport the salt towards the surface, because during this relative humidity cycle, some redistribution in depth of the salt was observed. Regarding the assessment of the damage, as mentioned, we try to keep this as easy as possible because to keep the test feasible. So we recommend visual and photographical assessment of the damage at each cycle. And for this description, we refer to existing atlas for damage definition. And also we add a qualitative scale of extension and severity of the damage. And at the end of the test, we require to quantify the material loss after separating the material from the salt. We are aware this is quite complex, maybe a little bit more time consuming than just recording the weight of the specimen and taking picture, but we find that is a more objective way to quantify the damage and so to rank the durability of the substrate. In the case no damages occurred, it might be possible to measure the salt distribution in the specimen to have an idea of the reason and also of the risk for the future for salt decay. So the procedure I described, we are now testing it in a round robin test. We are testing it on 8 different substrates, including limestone, sandstone, and bricks. And we are testing both sodium chloride and sodium sulfate. And regarding the laboratory, there are 11 laboratories who are working at the moment, testing different substrate and testing the procedure. And in a few weeks, we will have a meeting in which we will evaluate the test. So we will evaluate if the test is effective for all the substrates. So we know that it's effective for these 2 limestone, Mignet and Maastricht, but we wanted to know if now it's effective for a different range of substrate. So it means, is the test able to enables us to rank the substrate according to the severity of the damage? Is it possible to distinguish the effect of the salt amount we used on the damage? Are the selected concentration okay for all the substrate? Or maybe do we need to define the salt, to change the salt concentration depending on the material properties? Second question is if the test is reliable. So is the durability of the different substrate we test similar to what to expect based on the field observation? So a material which is salt resistant is also coming as salt resistant in the laboratory test. And is the type of damage we see in the lab, this scaling or spalling or these cracks, are they representative of the damage we observe in the field? And finally, as it is a round robin test, is the test reproducible in the different lab? Do we get the same results in terms of material loss, amount of efflorescence, and damage type? We hope we will be able to answer this question positively. And in that case, we can finalize the test and finalize the test procedure and publish it in 2022. So this was, thank you for your attention, and thank you to all members of the TC271 for the fruitful collaboration in the past 5 years. Thanks.